Am I sounding okay?
Yeah, we can hear you.
All right, good. All right, so we're getting into the last part of this course. So let me just show you on the calendar. All right, we're going to cover chapter 4. We'll start today, and it's all about logarithms and exponents. So hold on a second. So we got about 2 weeks, a little bit more to cover that, review, and have our last test before Thanksgiving holidays. And then after the Thanksgiving holidays, we got a week of we can review for the exam. I've tried to plan this out so that we can take full advantage.
Is the exam cumulative?
Yeah, it's a cumulative exam. All right, so let's get started on this, because like I said, I want to make sure we go through it rather with taking our time. If we have one section for each one of the days, it'll be a little bit more pleasant and slow, and hoping that they're going to get us into this new office soon in the new building, but because things just don't work very well over here, and everything over there hopefully will be fresh, but they're just now putting in computers. So all right, so let's get started on the stuff. We're just trying to see if we can get to who's here. All right. So the first thing is exponential functions. All right, an exponential function basically is f of x is equal to b, where b is the base, brought to some power. We could also say y is equal to bx. All right. Now b is a positive constant other than 1, so b's got to be greater than 0, not equal to 1, and then of course x is going to be a real number. Okay. So let's look at this first exponential function. This is just an evaluation of one, which is kind of the easiest thing to do with most of them. But we've got a function that says f of x is equal to 42.2 times 1.56 to the x power, models the average amount spent, and that's what f of x or y, or the output's going to be, the y, the old y, in dollars at a shopping mall after X hours. And then they just ask us, what is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Well, it's really pretty simple. X, they said, is the amount of hours. So we put in X for as 3. And then just to kind of show you what's going on, the problem is with the calculator. I guess most of y'all are using that one from 097. I'll use that one. That one's too complicated, and I don't think it's technically supposed to be used in that one, but I was just trying to use a basic one because they're all pretty much the same. Here we go. All right, so the way I would handle this is I would just, you got this thing, the x to the y function. So let's say 1.56 x to the y. So you're going to put in the 3, and then that gives you this part, the part to the right, and then you can say times 42.2. All right, so that gives us approximately 160. That's what the little squiggle means. So it would tell us that at the shopping mall, a 3-hour spree would be about $160. All right. Now, what does the graph look like? Well, what they're going to do is just pick points around 0. All right, it's really pretty simple, and they give us this one 3 to the x power. So that's what we'd call base of 3, and then the x is going to change. So they just put values around 0. I would have picked one more and put positive 2 also, but positive 2 is going to get real high. But watch how most all of these functions are going to work when the base is that whole number there. So when we put in -2, remember the negative sign takes the reciprocal and then we square it. So that's 1/9. And so for at -2, this little value right there is the 1/9. So it's getting very, very, very close, and it's just going to get closer and closer and never get there. So if you put in numbers like -10, it's going to be a very, very, very small fraction, but it'll never, never get down to 0 there because it's never going to touch that line. Now, all functions that, let's go to 0. All functions, exponential functions, if we put in 0 for the exponent, give us a value of 1. So all exponential functions are going to go through that point. All right, so then when you put in -1, that just takes a reciprocal and leaves a 3, so 1/3. All right, that's what this one is right here. See, it's not quite as close as the 1/9, but it's getting closer. And then they put in the 1, which is just going to be 3. And if we were to put in 2, it would be 9, which would be up here somewhere. So all the exponential functions have this basic kind of shape. They come out on that asymptote, getting very close on the left. They'll go through 0, 1, the y-intercept, and then they'll get higher fairly quickly. So they'll all have that shape. Now you can use that point right there, the 0, 1 is kind of how you would transform it. All right. In other words, that right there, 0, 1, and then we had 1, 3, and -1. This was the horizontal asymptote, y is equal to 0. So if we translate, in other words, transform. So in other words, if we fiddle with the x now, remember, that's going to be left and right shift. So that -1 right there, that's subtracted from the x, that means a shift to the opposite side of the negative. So that would mean +1. So this thing right here is going to go over 1 and be right there. Okay, that's the only shift that there is. They're not making this section too rough Let's see, there's the shift of 1 from the black to the red. All right, other than that, it's pretty much the same. Okay, now instead of being 0, 1, it's 1, 1. And instead of being 1, 3, it's 2, 3. So everything gets shifted over 1. The 0, 1/3 from the -1 to 1/3. So everything shifted over 1 on the X positively. All right, so this is just another thing to remember, that when you've got the one like the one we just looked at, it's the blue one. But if you got a fractional amount, in other words, that's what it means when it says between 0 and 1, that means that it's fractional. Then it flip-flops like this, okay? Just a mirror image on the Y. All right, now one of the most important things is this thing called, well, this is just telling you what I was telling you here. The domain is always going to be, and this is true for just about every function, the domain of a function is always, when I say function, I mean that it's actually a function and not just a relation. That the domain is always negative infinity to infinity, because you're looking at only the x-axis, so this thing is just going over and over and over and over all the ways it possibly can to the left, which is negative infinity, and then on the right, it's getting higher and higher, and it's just going to cover up the positive side. Okay. And then, as I've said, is for a base greater than 1, it's going to just go up just like the one we just looked. If it's between 0 and 1, in other words, it's fractional, then it flip-flops around like that. All right, now the thing that's different, and remember, in both cases, it never touches the x-axis. That's the horizontal asymptote. But just remember, now this is going to be the one case when we talk about next time about the logarithmic functions. The logarithmic functions never okay, it's recording. I was afraid I had to turn on the record. The logarithmic, it's the inverse, but it's a function as well. But we're not going to talk about that today. We're going to just look at these principles, and then we'll go through some problems from the book. All right. Now, the natural base E is very important in modeling things in not just mathematics, but in science as well, in many areas of science, because it mimics the behavior of many things that exist, well, naturally, for no other better word. Now, when you see this little thing E, see, it's a repeating decimal. It says approximately equal to. So what is going to happen then is, as this number gets higher, like if you put in 1 here and then just keep on going, it's going to get closer and closer and closer to this value. Like, for example, let's see, does this calculator have one? I know it does, but I'll just show you on this. I think this other one's got it. There's one calculator that I know I was doing in my other class, and it had the E on it, where you could just say, okay, well, here we go. Oh, you can only see it when it's bigger. Okay, so bigger. So see, if I just do e to the 1, in other words, it's that's just to the first power, then you can see how far out it goes. And that thing never ends. It's a repeating decimal. It's an irrational number. So it just keeps going on and on and on. And that's kind of what this tells us is the more times we expand it out with numbers there on the end, then it's going to get larger and larger and larger and larger. Just to kind of show you, if we put in 1 on that, so 1, and then 1 over 1 is just 2, and then we take that to the again, where's it? Oh, here we go. See, that's how it starts out, 2. And then if we did 2, if we put in a 2 for it, so that's 1 plus, and then 1 over 2 would be 0.5. Whoops, what happened? 1 plus 1 over 2. So 1 plus, I'll tell you what, I'll do it backwards. 1 divided by 2 plus 1. And then we're going to take it to the second power. There we go. See, it's starting to go out further and further. And we could do the same thing with 3. So it would be 1 divided by 3 plus 1. And then we're going to take that to the third power and see, whoops, what happened? So 1 plus 0.333, whoops. It doesn't like the mouse for some reason. Oh, that's how you get rid of that. 1.3333333. All right, and if we raise that to the third power, see how it starts taking out that shape. Now, we can put 4 and it's going to get closer and closer. So that's what that comes from, that value is 2.718, blah, 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 on and on. And the best way to do it is on your calculator, you've got that. I'll put this so it's on here. I thought I had been using this in this class. But if you ever need to have the value, pin the taskbar, there we go. Then what you would just do is just take 1 and take to the E, and that'll give you the value from the calculator. This is just showing you theoretically how that it's generated. And the more accurate, you know, the more decimal places you have, the more accurate it is. All right, so base E is going to be a very important one. You're going to see it over and over, and we'll also see when we see the logarithms, there's the opposite, the natural logarithm. All right, it says the exponential function f of x is equal to 1145 e to the power of 0.0325x models the gray wolf population on the Western Great Lakes. And f of x, the output, f of x, is however many years after 1978. So it asks us to project the gray wolf population in the recovery area in 2017. All right, so we got to figure out what x is, okay? We can't just throw in 2017. So we got to take 2017 and then subtract 1978 All right, so we're going to have X is equal to 39 years because 2017 is 39 years after 1978. So what am I going to do here? Well, I got to use my memory here because I'm going to take in and put 39 times, and I got to put in 0.325. Okay, so there's going to be my exponent, and I'll put it in the memory there. All right, that's usually the best way to do it, in my opinion. Now, we're going to take E, and again, the way this thing works, I got to make it bigger. If you got the regular calculator, then you can just do it. So we got to take E to the memory recall. So that gives us 0.04119375. Let me make sure I did that right. That doesn't look right. Because this, I'm doing it on the calculator so you can see it. For some reason, the mouse doesn't like it. All right. So 0.0325 times 39. Let me make sure I got that right. Okay, that's right. So now we're going to do E. Okay, there it did it. Okay, there we go. I knew it should have been bigger. Times 1145 is equal to 4,066.999. They rounded it off. So because you're not going to have a partial wolf. So that means that there's going to be approximately 4,067 wolves in that Great Lakes area after 39 years. All right, questions now. Just make sure when you're doing it with your calculator, I wouldn't just do it on the calculator, I would also write it down. All right, double check it, make sure you write it down, and then you can use the memory to put it in there, because you saw when I first did it that I didn't do it correctly. Let's see on this one. Let's see. So what they expect us to do is put in the value and then hit the E of X. Okay, and that does it. Most calculators are going to work like that. I'm kind of a bit used to the old Hewlett Packards that do it what's called reverse polish. Not that that means anything these days. So just remember, make sure you do it correctly in the correct order to get the value. And you can see it up there that it's telling that you did it, that it was E to this. All right. Like I said, I did that calculation separately and then double checked it to make sure it was right, the 1.2675. And then I brought E to that power. All right, questions? Because like I said, that's a lot of what chapter 4 is about. Okay, it's just going to be evaluating these. So you want to make sure you do your work correctly. All right, let's see. Did anybody else come in? Okay, I got it right now. Somebody comes in late, I'll deal with it later. All right, so y'all okay on this? like I said, hopefully this part is fairly easy because it's mainly just evaluating things. Now you do have that translation, transformation of the function, but they're not doing real difficult ones. So for the most part, it looks like they're just transforming on the back and forth on the left, right, or the up and down. And we'll look at a little bit of examples in a few minutes. All right, so let's get back and just go through the lesson here. All right, another one is called compound interest. Now, there's two different types of functions for compound interest. A really important function, especially like in the business world, if you're dealing with finance and such and accounting. But depending on how many periods that you compound per year, usually I think, like I said, there's not much of this going on these days because interest rates are so low, but usually what they'll do is they'll like compound quarterly, like 4 times a year. All right. And then the T just stands for the amount of time the balance is in the bank. And then the one, well, we'll see kind of how that works in. And then this is just the rate of whatever the rate is, like percentage, but you're going to use this as a decimal divided by the number of periods. And then, of course, you're going to multiply that by the principal, because this part right here is going to give you the increase over whatever time period you've got and however many quarterlies however many times you're compounding. But something that's much better or more accurate, and I don't know if that's probably what they do nowadays just because of computers, but you got this thing called continuous compounding. And this usually works out a little bit better, but the way it works is the amount that you're going to have in the bank is equal to the principal times E to the rate of return times the number of time it's in the bank. This one, we don't have to worry about the number of periods, compounding periods, because it's done continuously. All right, so let's just say a sum of $10,000 is invested at an annual rate of 8%. Now remember, you can't just throw an 8 in there because 8% means 0.08. And it asks us to find the balance in the account after 5 years with quarterly compounding, and quarterly just means 4 times, so n is equal to 4 there. So we got everything, we got to put the 10,000 out front, and then we got the 1 plus, and we got the plus 0.08. And again, what's happening is the 1 is giving us our principal back. And then this part right here is giving us essentially the increase at every quarter. All right, so then the 0.08 up there, divide by 4, and then all of that inside, and it's 4 times 5. So let's just look at that. All right, so we got 10. Let's do the inside first because that's going to be easier that way. I'll tell you what, let's work on our way out. So 0.08 divided by 4. All right, so that's 0.02 plus 1. So 1.02, and we want the y to the 20, 4 times 5. So 1.4859, blah, 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 on and on. It's not going to be a nice even number. It's just going to be a continuous. We're going to round it off to money. We're going to round it off to hundreds. So times the 10,000. So that's the $14,859.47. So if $10,000 sat in the bank for 5 years at 8%, which is highly unlikely these days, We'll probably get lucky to get half that, probably even less. For that 5 years, then there would be almost half, gained. In other words, it's not quite 5,000, but it's pretty close. $4,859.47 gets added to the principal. All right, now let's look at it in terms of continuous. Continuous. All right, well, no problem. I'll just, like I said, I don't like taking the role. If it was up to me, I wouldn't take it, but Delgado still has a policy. They want us to submit absences at the end of the year or attendance records. I don't use it. I mean, it's in the syllabus. I don't use it to punish your grade, but I do hold people responsible for anything they miss because, there's no way I can relate it to you. Now, I try to make the recordings, and as far as I can tell, I've recorded all of these sessions that we've met. So you can go back and look at it, but you can also catch up using the My Math Lab because you got information there. But I'm saying that's the way I see it. Okay, so let's just go to the board and work out some stuff. I got some problems here that I pulled from the book. All right, so let's take that one out. Everything's like going pretty slow. I don't see my little, oh, it's way up there. I mean, I got a pretty big screen here and I just still don't have enough room because these things like the little controls cover things up. All right, so let's say we want to, I'll tell you what, I'm gonna go look in a book here so I can get the instructions. I wrote down the problems, but I want you to have the instructions on them too. Wait, I'm not in the wrong course. What's crazy about this course and why it sometimes throws me for a loop is because Math 130 is almost the same exact class, except for a few little things. And they cover this too, but it's called chapter 3, and in your book, it's chapter 4. All right, anybody got any questions? Hopefully these things will kind of explain any questions you got, because I'm going to try to do things that contrast what I showed you in the lesson just a few minutes ago. Like they gave you a whole number for the base. What I'm going to do is I'm going to try to get one with the a fractional amount. All right, so that's what we're going to do. And thankfully, the graphing is not a big portion of this, but they do want you to see what the basic function looks like. All right, so let's see. I think I had. All right, we looked at one that is very similar to 11 or 12. And these 13 and 14, those are still greater than 1. So they're going to go more, let's take that shape, same kind of shape. But let's look at one that's actually a fraction. Let's look at 1/2. All right. So I'm going to take a little picture of this. And then I'm going to import it over there. I'm only going to deal with the one, number 15. But like I said, I like if you have the instructions. Okay, we're only going to look at this one. It's just kind of a matter of time because we got to actually put in some points and calculate. So let's do that. Well, it's actually it's h of x. Not that that's that big of a deal, but all right. So what I'm going to do is I'm going to pick 0. I'm going to pick 1. I'm going to pick 2, and I'm going to pick -1 and -2. And then I'm just going to evaluate. So h of 0 is equal to 1/2 to the 0, which is equal to what? If you don't quite know it, then let's watch.
Is that 1?
Yeah, because all of them are going to go through 1, 0, 1. So if you put in 0.5, which is 1/2, and you raise it up to 0, so you get 1. All right. So that's kind of a free point. H of 1 means we're just going to keep our base because it means that it's first power, which just means whatever the base is. All right, so let's do 2. And just in case, what this means is, it means that both numerator and the denominator get that exponent. It does not change the numerator because 1 squared is just 1. Okay. So this is 1/2. This is 1/4. All right. Now what's going to happen? Remember how when we did the one that was on the lesson there, the negative ones made it fractions, and then the whole numbers made them large. This one's just the opposite because it's the one that's fractional between 0 and 1. Okay. Let's see, where did they say that at? Yeah, here. See, when b is between 0 and 1, in other words, it's fractional. It's going to be symmetric about that y-axis. All right, so let's do h to the -1. See, and what this is going to do is it's going to flip that fraction upside down. Just like before, when we just had the 3. So this is just going to be 2. Because remember, what does the negative do? A to the -1. Well, the negative sign that just means so that's all it does. All right, the negative sign. So this right here, the reciprocal of 1/2 is 2 over 1 or 2. All right. And then -2, it's going to do 2 things now. The negative sign is going to take the reciprocal, and then the 2 is still there to square it, so that's 4. All right, and I wish this thing had some better drawing things, but I'm gonna just do a rough sketch because that's what they asked us to do. All right, so we got 0, 1. We got 1, 1/2, so right about there. And then 2 gets real close. And then over here, the -1 gives us somewhere right around in here. So that's 2. Probably off a little bit off scale, but all right. And then this is going to be jump up to 4. So 4 is right there. So then our rough sketch looks sort of like this. And then they say use a graphing calculator to see if you did it all right. So, all right, it's oh, there we got it. So to get it a little bit closer, but you see how it goes through -2 is 4, -1 was 2, and 1, this is 1/2, and then 2 is 1/4, and so forth. And then it's just going to get closer and closer. And then on the other side, it's getting higher and higher. And that's the effect of a fraction. All right. Now, next thing we want to look at is just one of these transformations. Like I said, they don't do both. They either use the X transformation, and then, like I said, that's the one where it's added and subtracted to X, and it shifts the opposite of the sign on the left or right. So if it's negative, it goes to the positive side. If it's positive, it goes to the negative side. And then the ones like this, where it's just added or subtracted, well, that one's true to the actual sign, means shift up 1. So let's just do let's see which one. See, all they're asking is just to select it, okay? So we've got 1 here, the basic one. That's the one that looks like this, okay? It's actually not going through 0, 1, so it's not that. All right, let's see if I can move out. So this one right here, let's see, this is 1 and 3. So this one right here, 22, is f of 3 of x, because see, we had just done that one on here. Remember, that was this one. See, it's got 1, 3, 0, 1, and then that's -1, 1/3. So this one, I'll tell you what, let me put that on the board over here. It makes it a little bit easier. All right, so I'm just going to write it on here. All right, so this is f of x is equal to 3x. All right. because of the 1, 3, and 0, 1. They'll all go through this. Now, this one right here is, okay, let's see, let's look at this 21. This one right here is this one projected downward. In other words, this is negative. Remember, the negative gives us the mirror image. So this is f of x is equal to -3 to the x. All right, so this one is shifted down somewhat. And instead of going through 0, 1, it's going through 1, 1 right there. All right, so what this one is the one that we looked at in the lesson there that I just showed you. It shifted over 1 to the positive side. Therefore, it would be this one. This one is this one right here. That's that same one we kind of looked at. So this is 3 to the x minus 1. See, because the transformation is on the x, it goes 1 in the opposite direction of the -1. And this is another one that's got a couple of things. Okay, first of all, it's, okay, we already got rid of this one. We got rid of that one. We got rid of that one. So this one has got to be a -1. And also the negative x is flipped around. So it's got two flips. All right. This negative x, all that does is just turn this one around to the side, and then the negative sign in front flips it down. So just like all the transformations we looked at, that's kind of how it works. Like I said, thankfully, they don't give you one that does both, but I'll just show you one real quick because I want to get another couple of applications. All right, let's just say I'm going to put a whole number in there. All right. Now, if we change and we put the transformation, that's going to move it 1 to the negative side on the x. See the purple? Instead of 0, 1, it's -1, 1. So I'm subtracting 1, the opposite of that. If we put 4 to the x, and then let's say we add 1, that's going to go up now. See, it went up. So what my advice is, always use the 0, 1, which is a common point to every exponential function, as where you do your shift. Likewise, if it were 4 minus 1, it's going to go down. See that? Up 1 for the +1, down 1 for the -1. And then that one takes the original function, this one right here. Take these out to see. And it flips across the x-axis. All right. All right, let's look at a couple of applications. Oh, we got time. Those are kind of can be a little bit time consuming. I mean, the graphing is a small part of it, but it's not a major part. The major part is doing the actual calculations on these things and figuring out what they are. But let's go over and look. All right, on the book. All right, let's see. I want to do like what's back on 54. All right. So let's look at this. I'm going to take it and put it over in the on the board there. Oh, who is iPhone? I forgot. I mean, I probably should know it, but it's a good thing to know because I just saw the message and so just type it in the chat so I know because I don't really have a clue offhand. And like I said, it's during this time of year. I mean, it's hard to keep up with. Even if I know something, I'll forget it. But anyway. All right. So we got three things to do. All right. What does semi-annually mean?
Twice a year.
Twice, right? Okay. And then our rate. I'll tell you what, let's put the rate here. All right, that's important because remember, you got to use the decimal, see? And if you put it back, 1, 2, see it's 6.5. So make sure you put in the zeros and all that, right? So now we're going to put all right, and then we got 1 plus 0.065 over 2. And then it's 10, it's up here, it's 2 times the period, which is n is equal to 10. I'm sorry, not n is equal to 10. It's t is equal to 10. And let's see. They're giving, and that's the formula that we're using right there, okay? I didn't write it down, but that's it. All right, so when we do this, this is going to be equal to 5,000. And like I said, the way I would do it on my calculator is take the 0.065 0.065 divided by 2. All right, and then add that to 1. That's my base, and I'm going to raise it to the 20th power. All right, so that's going to give us, wait a second. Did I do that right? No, I sure did, didn't I? Times. So that gives us 9,000. So this right here is just going to be, what was it? It was 1.89. And remember, as far as rounding off, they say to go to the nearest cent, but always go a few places past what you want to round off to until you get to the very end and then round off. Because once you lose accuracy, you can't get it back. All right. So that's A. B, I'm going to do it real quick. Let's see here. It's just kind of a pain in the neck with the mouse. Probably even if I had a touch screen, I don't know if it'd been better because I had a touch screen earlier. And so the only thing that's going to change is now this is quarterly. So it's going to be 4. That was a 20. So now it's 4 times 10 because this was a 2 times 10. All right, so again, it's going to slightly change because of the compounding. We got 0.065 divided by 4 now, plus 1. And then we're raising that to the 40th power. All right, and that gives us 1.9 times 5,000. And notice it's not changing a great deal, but the more you compound it, the larger that number gets. And again, I'm going out past what I'm going to round out to, because if I were to just go out to a 1.9 and put a 1 there, then I'm going to lose some accuracy and it may not match what the answers are. Okay, and then this is 95,027, and then round it off. To 79. So see how it's getting larger? And then if you calculate, and I'm not going to go through the whole thing because I want to do one more of the kind of, well, I don't know, we might not need to worry about it. I had another one here I wanted to do, but we got 4 parts to this, so we're gonna have to rush, because basically they're all the same. It's just you're just pumping things into the x, and then for this we've got various exponents that are changing, and then we'll do it with the e function, the e exponent. All right, now it's 12, and then it's 10 times 12 now. Because remember, the t is 10, and hold on a second. 2 times 10. So the t is 10. Oh, and the n is changing. So this was, let me put this in here. This was n is equal to 4 if you didn't see it. And then this is n is equal to 12. So the t is always 10. I didn't write it there, but 2 times 10 is 20. So this is going to be 120 now. I'll just write it below that. So it's a larger power, but it doesn't change it a lot. Look at it. Okay, so let's look at that. So we got 0.065 now divided by 12 plus 1. There's our base, and we're going to raise it to the 120th power. So it's 1.91218. It's a little bit higher, but not a great amount higher. It's just showing you the effectiveness, or how the compounding, the more you compounding, the greater the total principal is going to be. 1.91218. All right. And then what does that comes out to? That comes out 9,560 now. See, each one's gotten a little bit higher, and 92 cents. Okay, the last one's actually an easier calculation because we're using the function over here, the PERT. The way I always remembered that was PERT, that it spells PERT. All right. Okay. So all I'm doing is I'm taking P times E to the RT. I don't have to worry about an N here because it's not being broken up into intervals or into compounding periods. It's compounded continuously. All right, so this is going to be 5,000 times E. The R is still 0.065. And now notice that it's in the exponent now, times T of 10 years. All right, so let's go ahead, back to the little calculator thing. Okay, there's my exponent. So I'm gonna put it in the, let's see, wait a minute. I think they went like this, right? Yeah, there we go. So that's 1.9155. I don't know why I said is I keep wanting to do it backwards because of the old HP calculators. 1.1, 1.9. And then that comes out to 95 or 9,577 and 70 cents. And you see that that is more than any of the other ones, because when you compound continuously, you're taking interest that you've already gained and immediately, putting it into the principal. All right, any questions? All right, so just for time's sake, I'm not going to fly through another one like this because these are really the pretty easy ones, because all you're going to do is just pop in something for X, multiply times that, take the E to that power, and then multiply times that coefficient. Okay, those are all pretty much the same. I really wanted to work this one because it had 4 different parts. All right, so